Hello. So, my name is Julianne Chen, and today I'm going to be talking about electrochemical impedance spectroscopy for my MATSE504 final project. So, let's get started. In 2022, this Tokyo team demonstrated superionic conductivity of magnesium ions in ambient temperatures in a new material called metal organic frameworks. And so, this new solid state material is made of these metal clusters. Here it is the chromium ions connected by these organic ligands in the gray, which are terphthalic acid, for instance. And so their structure is based off of this classic MOF structure called MIL 101, in which their pores are up to 32 angstroms wide. And so that allows them to actually form these TFSI channels to allow for the magnesium ions to go through, allowing for magnesium superionic conductivity. And so this is very interesting because normally these divalent ions have a very large charge, like 2 plus, and the fact that they are very large impedes the mobility of our ions. So that's why normally lithium is chosen because of its very small size and because it has a 1 plus charge. And so in this study, they ended up using a 2-electrode setup with electrochemical impedance spectroscopy to measure the resistance of our sample and the counter electrode, and also of the magnesium 2 plus bulk conductivity, which was record breaking at the time of 1.9 times 10 to the power of -3 Siemens per centimeter. And so let's keep this study in mind while we divulge into the characterization technique. So to explain EIS, let me give you an example. So imagine I have this black box of unknown composition and properties. If I were to shine a specific wavelength of light and there is some kind of response, the material could be photoactive. Now, if I want to know the kinetics associated from the discharge of current from the absorbed photon, I can find that out by modulating my light intensity. And so the relationship between our input and our output is a transfer function, and that is the fundamental of EIS. So EIS is basically when we use an AC or a DC signal to perturb our solid state or equilibrium system, and then we measure the sinusoidal response. You can think of this as having it be equivalent to an electrical circuit, where these different parts, our properties, can have different timescales that they operate at. And so by using this wide range of probing frequencies, we can end up determining these different properties, such as, for example, using a low or slow frequency can give us more information on the slow diffusion process. Now, if we use high or fast frequencies, we can actually measure the fast charging and discharging process at the interface of an electrolyte and a cathode or an anode. And so using EIS, you can get, once again, a bunch of different properties to measure. So you can have the double layer capacitance, the depletion layer capacitance, your carrier mobility, your surface states, your composition, your bulk conductivity, or your grain boundary conductivity. And so in order to use EIS, we need to conform to a bunch of different assumptions. So number one, we need to follow the Kramers-Kronig transformations, meaning our system needs to be in equilibrium or in steady state. And so we need to make sure that our system doesn't change with time, as if it does, that means our measurements are not accurate. Secondly, we need to have a linear response to perturbation. And so, as we know, current is nonlinear, a nonlinear function of potential. So for specifically electrochemical systems, for instance. And so if we use a small enough input, we're actually able to express the current as the first term of the Taylor series expansion, meaning that it will be a linear response. And so we need to find this amplitude by basically experimenting and then using either direct integration or using these modern regression models that extrapolate to zero and define our infinite frequency limits as shown here. And so another way to think of this is the fact that the sinusoidal response has to be a phase shift of our actual original perturbation. And so number three, we need to make sure that our system is stable. So our response cannot grow with time, or it needs to be in steady state and decay to a new steady state value if it decays. Number four is causality. And so our response cannot occur before we perturb our system. And this basically allows us to correlate our input with our output to be able to determine our properties. And so because our measurement times for EIS can be from minutes to hours, if we have any non-stationary behavior, this can lead to the breakdown of causality, meaning our measurements are no longer valid. And so when we are actually setting up the measurements, we have either 2 to 4 electrodes. So the working electrode is your sample, and your counter is basically opposite to your sample. And then the reference electrode is basically studying your sample's response independent of the processes taking place at the counter. And so when you use a simple working and counter two electrode setup, your response is not individually separated, meaning that your response is a sum of all the contributions in the system. So this is typically not used unless you cannot insert a reference. So this is like a battery or a fuel cell where it's not easily inserted. We usually use 3. So the reference, once again, helps separate the responses of our sample independent to the counter electrode. And of course, for a 4 electrode setup, this is usually to measure our electrolyte conductivity for freestanding films, or even for measuring the interface between immiscible electrolyte solutions. And so these 2 reference electrodes on either side of the interface is measuring our potential while the other 2 electrodes pass the current. And so this really prevents the confusion of our working and counter impedance responses. And so this is an example of a standard EIS procedure. We have applied some kind of AC electric field. We then measure the output current. And then finally, we actually calculate impedance by doing E over I to get our impedance. Impedance can then be broken down into 2 terms, Z prime and Z double prime, which is a complex number, and that represents the phase shift of our linear response. And so once we have our impedance, we actually fit that to an equivalent circuit. And so an example, the most simple representation of an electrochemical interface is the simplified Randall cell. And this is basically a resistor in series with RC parallel circuits. And so this might not be accurate for complex systems, but RS is basically our solution resistance in series to a parallel combination of our resistor, RCT, which represents the charge transfer resistance, and CDL, which is our double layer capacitor or our electrode capacitance. And so taking our measured impedance and we fit it to the equivalent circuit, we can actually form a Nyquist plot. And so this is once again, the 2 parts of impedance, which is the real and the imaginary. And so at each frequency along this semicircle, we have an amplitude of Z and we have a phase shift of phi. And so at our low frequencies, we can actually find the resistance and also our resistor. And at high frequencies, we can have the resistance of the solution in an electrochemical system. And so these are 2 very big aspects or properties of our electrochemical system that are found just by making the plot in itself. And of course, there are more calculations you can do with the data collected. So you can actually measure, once again, our impedance, our admittance, our permittivity, our electric modulus, and we can even measure the conductivity. where R is our resistance, we have C as capacitance, and we have G as conductance. And so, to give you more examples of real-life applications, this is another Nike's plot using EIS data, except they have actually included more than just the characteristic semicircle shape. So, in this graph, we can see that the characteristic relaxation frequency is the highest point of our Nike semicircle at around 1.6 kilohertz. And so that means that this is where the impedance response is dominated by the charge transfer reaction at the electrode-electrolyte interface. And so using the characteristic relaxation frequency, we can actually use that to find the characteristic time constant tau, which is used to assess the rate of reaction at the electrode-electrolyte surface. And so a higher tau basically means that we have a faster reaction occurring. And so in this Nike's plot, they also have this low frequency straight slope. And this is actually the Warburg impedance of mass transfer, meaning this is the electrical impedance of ions diffusing at an electrode's surface. In other words, this is the diffusional resistance to mass transfer in the diffusion layer. And so when we're doing our measurements, we also usually take these Lissajous curves. And so this helps us validate our measurements in real time, where this is a normal Lissajous curve, right? At 20 hertz, where it is a perfect ellipsis. And if there is any kind of distortion or degeneration, for example, here, that means that we have some kind of non-linear or non-stable system. And so that means that our perturbation amplitude is way too large and is not giving us a linear response. And so if any kind of distortion occurs, we have to redo our measurements at that specific frequency. And so, as you can recall, in the previous slides, we talked about the MIL 101 TFSI electrolyte. And so one of the big issues that they ended up facing was the fact that they couldn't insert a reference cathode. And so they only had a 2-electrode setup when they did EIS. And so because of that, remembering that the response is basically a sum of all the components in our material, they were not able to determine if their conductivity that they measured was of our bulk or if it was because of grain boundaries. And so they needed external validation, such as measurements with and without certain vapors that didn't actually vary in their conductivity values to basically confirm that this value that they ended up finding was for the overall bulk conductivity of our material, not just along these grains. And so EIS is a powerful tool, but it does have limitations in real life solid state material characterization, such as in meta-organic frameworks. And so at Penn State, we actually do have quite a few EIS machines on campus. So we can have of less than 1 millihertz all the way up to 1 megahertz. We also have these very cool machines that can do basically a temperature sweeping from a -60 to 300 degrees Celsius temperature range. And so that is basically the very short form version of electrochemical impedance spectroscopy. Thank you so much.